Hello.
Okay. For members in the room because I'm in cover company.
Okay. Good morning, everybody, I guess. Our only morning lecture. All right. So the topic of today's lecture is behavior trees. So we talked about implementing behavior in terms of finite state machines in the previous lecture. And so in this lecture, we're going to talk about a different way to implement behavior, and this time using something called a behavior tree. All right, so a behavior tree is similar to a finite state machine, right? They're both models of a plan of execution. Behavior trees and finite state machines, it turns out they're very commonly used in robotics, and now both are commonly used in video games. It's often the case that something shows up in robotics first, and then that same idea shows up, or a related idea shows up in video games. At least it's published first in robotics, and then it shows up in video games. It's entirely possible that some video game programmer somewhere has invented a bunch of these techniques, just never published. Okay, so we know that in a finite state machine, basically you're building up your state machine using states, right? So there's a finite set of states and there's some transition between states, right? The finite state machine is simply describes how you switch between each one of the states. In a behavior tree, your building block is what's called a task. Now, a task is just some computation. That's all it is. Sorry. So in a behavior tree, your building blocks are tasks, and the behavior tree describes switching between a finite set of tasks arranged in a tree. Right now, in a state machine, you've got a graph, and in a behavior tree, it's a proper tree, right? Directed acyclic graph, if you want to call it that. Right? And so the idea in a behavior tree, because it's a tree or it has a tree-like structure, the structure is recursive, right? So you have a simple task and you can compose a bunch of simple tasks together and make a little tree out of it, right? And that little tree now represents a more complicated task, right? And now you can take a bunch of subtrees, mash them all together, and you've now got and yet even more complicated task, right? And now you can take a bunch of those subtrees, mash them all together, and you've got even more complicated tasks, right? So, and so on, and so on, and so on. And so this is one of the advantages of using a behavior tree over a state machine, is that you can define tasks and they are potentially reusable, right? You can compose them into more complicated tasks, and the more complicated tasks are potentially reusable, and so on and so on and so forth. It turns out that there is a one-to-one mathematical relationship between a finite state machine and a behavior tree. So in fact, anything you can do with a behavior tree, you could technically do with a finite state machine. Anything you can do with a finite state machine, you can technically do with a behavior tree, but it's often easier to think in terms of one or the other, depending on the task that you're trying to, or the problem that you're trying to solve. There's an example of a behavior tree. It's a tree, right? No surprise. It's not a binary tree, right? So it's an actual, it's a general tree. We'll come back to exactly what this tree is trying to show you or trying to describe later on in the lecture, right? That's just showing you what a simple behavior tree might look like. Okay, so your tree made of a bunch of nodes, right, which you can see here, right? Each one of those nodes is just called a task, right? You could just call them a node. It depends on what reference you're actually reading. Most of the literature on behavior trees call these tasks instead of nodes. The nodes are just tasks, right? Tasks are just nodes. In a behavior tree, a task is able to inform its parent of its status, right? And so that node there can tell its parent node what is the status of this node, right? Similarly, that node there can inform its parent of its the status of that node there. And so for your statuses, you can use whatever you want to indicate the state of a node, right? Status, state, right? State of a node. So a simple behavior tree, your statuses might just be success and failure, right? So true and false. Typically, though, a behavior tree for video games uses at least 3 statuses, right? So success, so true, failure, false, right? And running, indicating that your task is still running, right? It hasn't determined whether or not the task has succeeded or failed yet. It still needs more computation time to figure out whether or not it's going to succeed or fail. So this is a pretty common implementation of a simple behavior tree for video games, right? So 3 states for each task. So an example of this might be a walking task, right? So you want to walk an object from one location on the map to another location on the map, right? In principle, we know how to do this, right? So while the task is running, what does it need to do? Right? Well, it might need to do some pathfinding, right? That might take some time depending on how complicated your map is, right? Once it's figured out a path, it now has to actually walk the object across along the path. So it needs to do some steering and some collision avoidance, right? If the path is very long, this task is going to take a long time to complete. Right, if the path is very short, it may only take, only need a very small amount of time to complete. Right, but while it's performing all of these steps, its status is running. Right? So when does the task succeed? Well, the task succeeds when you actually manage to walk the object to its specified location. And when might it fail? Right, so it could fail if the target location is unreachable. Right, so in other words, if pathfinding fails, you could have failure. Right. If you're implementing a game and your object that's walking can die, right, and it dies along the route, right, so it encounters some complication that causes it to stop or divert from its path, you could end up in a failure state there. Okay, so in these behavior trees, there's no actual standard way of saying what kind of tasks are in the tree. But this is a common set of tasks that you'll see in most behavior trees used for video games. And so a task can be a condition. So this is essentially something that's true or false, right? It can be an action, and it can be something called a composite. And your composites can either be selectors or sequences. And so we'll look at all of these tasks now in detail. Okay, so what's a condition? So a condition is one of the leaf nodes of your tree, right? So in other words, it's one of the terminating points on your tree or one of your terminal nodes on a tree, right? And a condition is something, it simply tests the property of the game, right? So it's something that's essentially true or false, although it can also be running if the test takes a long time to run. Right? But the easiest way to think about this is something that's true or false, right? So for example, you can test proximity of an object to some other object. Right? So for example, is your object within some distance to a specified target? That would be an example of a proximity test. Right? You can have line of sight tests, right? Does the object have line of sight to some specified target? Yes or no? Right? And of course, state tests are very common, right? Does the object have some particular property, right? Does it have enough health? Does it have enough ammo? Does it have enough money, et cetera, et cetera, et cetera, et cetera. Right? So anything where you might want to know a true or false answer, that would probably be a condition or would be a condition task in your behavior tree. Now, I will point out right now, very briefly, some popular behavior trees don't have these nodes. So they don't have condition tasks. They do it a different way. But there's still a way to test whether or not, to test some property of the game in those types of trees. Okay, so these tasks, obviously they're going to return success if the condition is met, right? They will return failure if the condition is not met. In some cases, they might return running if the test takes a long time to run, right? But typically these tests are very fast. So they are either return success or failure. Okay, so the next type of leaf node is an action, right? So your leaf nodes are all conditions or actions. An action is a leaf node that alters the state of the game somehow. In other words, it performs some kind of action, right? So you could have an animation or some kind of movement, right? So if you're going to move your character across the screen, that would be an action. Across the map, that could be an action. If your object opens a door, that could be an action. Right? Anything that changes the state of an object could be an action. Right, so if your character equips a tool or a weapon or something like that, that could be an action in your tree. Right? If you need to perform some sort of AI task or some sort of physics task, right, that might be an action on your behavior tree. Right? So for example, pathfinding could be an action. So actions return success when the action is completed. Right? They fail if the action can't be completed. Right? And they return running while the action is processing. Right, so again, tasks, they're just computational tasks, right? Some tasks take longer than others. If the task takes a long time, it might return a running state, right? So moving across a map, for example, could take a long time, right? So it's not unreasonable for an action task to return the running state. Okay, so what about your internal tree nodes? So your internal tree nodes are probably made up of composites. So your composite nodes are simply parents of subtasks, right? Because they're the internal nodes of your tree, right? Your internal nodes are responsible for running all of their child tasks, right? So in other words, a composite node basically manages its child nodes, right? That's the easiest way to think about it. Now the question is how does the composite manage its children, right? And furthermore, what does a composite node return, or what is its status? Right. So again, the internal nodes, they all have three statuses. So success, failure, and running. Right. But the status of an internal node depends on the statuses of its children. Right. So for example, some composite nodes will fail if any of their children fail. Right. Some will succeed if any of their children succeed. And you can cook up all sorts of different types of composite nodes depending on exactly what your children, what the status of your children are. We're going to keep things simple, and we're only going to talk about two kinds of composite nodes. Right? Okay, so the first kind of composite node is called a selector. Right? So a selector basically selects the first successful child task. Right? So the way this thing works, so it returns success if any one of its children runs successfully. Right? So the simplest way to think about this thing is you've got an internal node, it's got some children. It runs each one of the children in turn. Right? So starting at the left, right? It runs the leftmost child, right? If the leftmost child succeeds, the selector also succeeds. Right? If the leftmost child fails, the selector doesn't automatically fail. It then runs the next child in the sequence. Right? So then it runs the second child. Right? If that one succeeds, the selector succeeds. If it fails, it runs the next child, and so on and so on and so on. Right? Eventually, if it runs out of children and none of the children succeed, that's when the selector fails. Right? So an example of a selector task. So selectors are used to choose the first of a set of possible actions that will succeed. right? So an example of this would be you're implementing the AI for a character, and that character is trying to reach a safe location somewhere, right? And so you can imagine this is one of your shooter type games, right? And so the first course of action that you might try to take is you might try to find some cover, right? If that fails, you don't immediately give up, right? You try to do something else. So now you try to leave the area, right? If for some reason you can't leave the area, you call for backup. Hopefully backup can airlift you out or something, right? And if that fails, finally your status is failure, right? All of your children failed to produce an action that caused your character to reach safety, right? Therefore, the selector, the parent task now fails. Right? And so there's an example of what your selectors look like in a behavior tree. Right? So it's very common to see a selector be labeled with a round circle and a question mark. Right? So if you see one of these, that's a selector node. Right? For the example that we just described, it has three children that are all actions. Right? So the first action is try to take cover. Right? If that fails, try the second action. Right? So we're going to try to leave the area. If this one fails, right, we're going to call for backup. And if this one fails, right, finally, the selector node fails. Right? If any one of these succeed, the selector node succeeds. Right? The easiest way to think about this is that the child tasks are run in sequence, right, from left to right. But that doesn't have to be the case. Right? But that's the we'll think about it in this way for now. Right? So internal node, right? Leaf nodes are all actions. They could also be conditions. Sorry, they could also be conditions as well, but in this example, they're not. Right. Okay, so choose the first of any one of the child tasks that succeed. Right. There's also something called a sequence composite node, right, or a sequence task. So a sequence task returns failure when any one of its children fail. So in other words, this is what you're going to use when you need to perform a sequence of tasks to complete the overall task. Right? Failing any one of the intermediate tasks causes the overall task to fail. Right? So this is what you use when you perform a series of tasks, all of which need to be performed to complete the final task. Right? So the easiest way to think of a sequence is that it runs each child task in turn until one of the children fails. Right? If all of the children succeed, the overall task succeeds. Right. So, for example, you want to write a sequence that opens a door, right? And this is assuming that your character or the object is already in front of the door, right? So, what do you do to try to open a door? Well, you're going to check, is the door unlocked, right? If the door is not locked and you don't have a key, you're going to fail, right? There's no way to get through this door, maybe, right? Otherwise, right? So if the door is unlocked, you can open the door, right? You've now successfully opened the door, so now your status is a success. Right? And so that's what a composite sequence looks like. Right? It's an internal node. It's very common to see it labeled with a single arrow. You have to be careful here. There's also a task that have multiple arrows. The single arrow typically means sequence. Oh, sorry. In this example here, our leaf nodes, one of them is a condition. Right? So is the door unlocked? True or false? Right? If it is, open the door. So the way this thing works is, right? Is the door unlocked? If the status here is success, so yes, the door is unlocked. It now runs the next child task, right? Open the door. In this case, opening an unlocked door always works. So this succeeds, and now the overall task succeeds, right? If the door is locked, this returns failure, and now your sequence immediately returns failure as well. So again, the easiest way to think about this is that you're going to run the tasks from left to right. That's why it's called a sequence, right? If any one of the subtasks fails, your overall task fails. Okay, so how do you build one of these behavior trees given our four kinds of nodes, right? And so typically what you do is you don't design the whole tree all at once, right? You think about the overall behavior that you want to implement, right? And so, for example, here we want to build an AI or an enemy that moves into a room to chase the player, right? So the AI character is outside of the room. there's a door leading to the room, right? Or doors leading to the room. In this simple case, we're going to talk about one door, right? So your overall action, move into the room, right? Okay. Now, if there's a door on that room, right, this doesn't work, right? If the door is closed, right, that task fails. You can't move into the room because the door is closed, right? So now you want to take care of the case. Okay, so what happens if the door is closed, right? And so now you expand your tree, right? And so so we're going to use a selector to deal with the case of whether or not the door is open or closed, right? So here's our selector, right? The selector has two children, both of which are sequences, right? So the first sequence is made up of a condition, right? Is the door open, right? Which is the door open, right? If it's open, so if it succeeds, move into the room, right? If the door is not open, right, that fails, which causes the sequence to fail, right? That doesn't cause the selector to fail. It causes the selector to run the next sequence, right? So the next sequence runs, right? Now we move to the door, right? So remember, you're in a room and the door leading out of the room is already open. You don't have to go to the door. You can just move into the room, right? Okay, so now you've got a closed door leading to the next room. So you want to move to the door, right? You want to try to open the door, right? And then you want to move into the room, right? So if any of these fail, then the sequence fails, and the selector will fail at that point, right? So if you look at this set of moves here, moving to the door could fail if there's no path to the door, right? Let's assume that there is. Okay, opening the door can fail if the door is locked, right? So we're going to expand this node to deal with locked doors, right? So here we go. So there's our selector. Here are our two sequences from before. And now we're going to insert another selector, right? So we move to the door, right? You now want to ask the question, is the door locked or unlocked? Right? So we're going to use a selector here to deal with those two cases, right? The selector, its children are both sequences, right? One of the sequences deals with an unlocked door. The other sequence deals with the locked door. Right? So the sequence on the left deals with the unlocked door, right? So is the door unlocked? If it is, open the door, right? So if this succeeds, open the door. That's going to succeed because the door is unlocked, right? That causes the selector to succeed, right? That causes the sequence to now cause the character to move into the room. Right? Okay, so suppose the door is locked. So this condition is false, or its status is failure. That causes the sequence to fail, which causes the selector to run the next sequence. Right? So the next sequence asks, is the door locked? Well, the answer is yes, because the door was unlocked over here. Right? So if the door is unlocked, knock the door down. Right? So try to barge the door down. Right? Assuming this succeeds, that sequence now succeeds, that selector now succeeds, and now you can move into the room. Right? So either way, you either opened an unlocked door or you knocked down a locked door. Right? If you had a key, or if your character could have a key, you would put in that case here as well, possibly. Right? So you'd insert another sequence. Oh, there's something important about the order of these, the way the tasks are put into the tree. Right? So when you're putting the tasks into the tree, the order in which you put things in is important. Right? You want to make the tasks that are easiest to perform to the left of the tree, right? So in other words, you don't want to flip these two sequences around, right? So you want to test, is the door open first? Because if it is, you can just move into the room, right? You don't want to have to go, so you don't want to have to evaluate all the stuff in the right subtree first before going to the left subtree, right? Similarly here, right, when you're dealing with the door that's possibly locked or unlocked, right? You want to check, is the door unlocked first, right? And if it is, go through the door, right? You don't want to bother checking, is the door locked first, and then knocking down the door before trying to go through the unlocked door, right? If you flip these two around, if you flip these two around, so it's easier to evaluate, is the door unlocked and go through the door than it is to evaluate if the door is locked and then knock down the door first. right? You always want to put the tasks that are easier to perform to the left in these kinds of trees, right? In other words, you want to try the easiest things first before trying the more difficult things. Okay, so our composite tasks are all sequential. They all evaluate the children in a particular order, right, from left to right. But in many cases, that's not necessary, right? So in many kinds of composite tasks, the order of the child task is important, right? But it's not always the case, right? If you add some randomness in the order in which the child tasks are performed, that leads to less predictable behavior, right? It leads to more natural behavior in the behavior of the objects that you're trying to control. Right? So in other words, they're not always doing the same sequence of things to try to accomplish a task, right? They can try to do things in a different order, right? So sticking with our example here, so we've got we're trying to implement an AI for an enemy chasing a player, right? So when they encounter a locked door, instead of knocking down the door, maybe we want to add some other action instead. So for example, suppose we try to smoke out the player from the locked room instead, right? Okay, so you come to a locked door and now you've got a choice, right? You either knock down the door or you can light the door on fire, smoke out the player. Both of these seem difficult to do, right? So furthermore, if you always try to knock down the door first, right, you'll never try to light the door on fire. If you always light the door on fire, you're never going to knock down the door. So this is an example when you want to randomly choose between the two types of subtasks. Right. So here we want a selector that can randomly choose between in this case, two different subtasks. Okay, so here's the part of the tree that deals with going through an open door, a door that's already opened, right? This is the part of the tree that deals with opening a closed door that's not locked. Now here's the part of the tree that deals with a locked door. So here we want a selector, right? And we want to choose between knocking the door down or smoking the player out, right? We want to do this at random. So a random selector typically has a twiddle in front of it or a wavy line through it. Right. So it's either a tilde question mark or a question mark with a tilde through it or something or some funny symbol indicating that that this is a random selector instead. Right. So this selector here will randomly choose between one of these two values. How you implement the randomness is up to you. Right. So there might be some percent probability you do this, and there might be some corresponding percent probability you do this. Right. Could be 50-50, right? It could be prefer to barge down the door, knock down the door, as opposed to lighting the door on fire, right? It's up to you how you implement this. Okay, so how are you going to implement this smoke out task? So for the smoke out task, you need to light the door on fire, right? And so to light the door on fire in your game, you might need the enemy to have some matches and some gasoline or some sort of accelerant, right? So you now might want to put in some AI that has the enemy go find some matches and gasoline. It doesn't matter what order they get the two things in, right? It doesn't matter if they get the gasoline first and then the matches, or if they get the matches first and then the gasoline, right? So here you want a sequence task that can randomly choose between the two different tasks. Right? So here we want a sequence that does not necessarily evaluate its children from left to right. Right? And so the way to indicate a random sequence is with the arrow and then draw some squiggly lines through the arrow. And so that's a common notation in these sorts of behavior trees, right? And so this sequence here tries to get some matches or tries to get some gasoline, right? Sorry, and tries to get some gasoline, but the order in which it does this in is random, right? And so now when you evaluate this tree, right, can we enter a closed, is the door already open? If no, the selector tries to go to the next case, right? Can we open the door? Can we open the closed door, right? If it's locked, we end up over here, right? And now we randomly choose between these two options, right? If we choose the barge the door, knock down the door option, right? And this succeeds, then the selector succeeds, right? If for some reason we can't knock down the door, you're going to choose the other option, right? Burn the door down. But this happens at random, so you might choose the try to burn the door down option first, right? So when you go to the burn the door down option, right? the first thing you're going to do, you have to make sure you have matches and gasoline, right? If this fails or this fails, right, that sequence fails, which causes this sequence to fail, which causes this selector to choose the other option if it hasn't already chosen it. Right? If it's chosen this option, this selector now fails. If this sequence succeeds, you're now going to light the put the gasoline on the door, then light the door on fire. Right? Now the selector succeeds, or sorry, now this sequence succeeds, which causes that selector to succeed, which causes the topmost selector to succeed. Right? And so there is an example of a building up a behavior tree, starting with the most abstract action. Right? So starting all the way back with the simplest action, moving into a room. Right? You can add increasingly complicated behavior, right, to deal with more and more cases that you might have to deal with in your game. Okay, so where are behavior trees used in actual games? So Halo 2 was one of the earlier games where the developers let it be known that they were in fact using behavior trees to implement this behavior in their games. So this was in 2005, so roughly 20 years ago now. There's a little video. It's actually, sorry, it's a long video. It's like an hour and a half. I'm only going to play 3 minutes of it. So this is written by the lead it's a presentation given by the lead AI programmer for Bungie games. It was presented at a game developer conference, so GDC, which is the largest conference for game developers. It happens every year. So there's a GDC 2025 happening next year. Okay, so this is the lead. This is the lead AI programmer for Bungie talking about behavior trees in Halo 2. You're going to see it's a little bit different than what I described here.
Behaviors to choose from. Well, I choose engage. Now I have these options. I decide search because I can see the guy, and then I decide what kind of search, and it's uncovered. So very simple. Here I'll get a little polemical. I mean, like one of the problems I think we have in the game industry is that we tend to reinvent the wheel over and over again. And in particular, hierarchical decision structures is something that everyone's using and everyone's calling by a different name. So I apologize if any time further on it. But as it is the fundamental decision structure of the Halo 2 AI, I have to do it in some way or another. So we also have good things about it. Sort of intuitive way to think about decision making, fairly modular, and it's nice and scalable because I'm branching a tree and I don't have to think about all the other branches going down one particular branch. The bad thing is, of course, that it's never really that simple. Though I've implied all kinds of modularity and encapsulation and so on, there is all kinds of subtle communication going on that we can't really get rid of. Debugging is hard, often because we're not debugging in terms of why did the guy do something, but why did he not do what I expected him to? Sort of negative debugging. And also memory is hard. And I'm going to talk a lot more about memory later on.
Okay, there's some important points there. So there's lots of terms that he just used there that you should all be familiar with from your 4 years of computer science education now, right? He's talking about encapsulation, reusability, scalability, and things like that. So those are all principles that are supposed to be taught to you in software engineering at some point, right? There's some other things he's talking about here. So notice that when he went through his tree, right, he kind of randomly picked the actions from the separate layers in the tree, right? So starting at the root, he randomly picked engage, and then he randomly picked search, and then he randomly picked uncover, right? So in our discussion, we would evaluate the children from left, I guess from bottom to top, right? But there but it is often useful to evaluate the children randomly, right? Whether or not you can do that depends on exactly the kind of behavior you're implementing. So I'm going to come back to this in right. So we can revisit that in the lecture in just a bit. The debugging point is interesting, right? So his point is that how do you debug this sort of thing, right? Well, you have to run your tree, right? So in other words, you got to run your game and then see what happens, what actions your character is taking as they go through the tree, right? And you might find, so it might produce some reasonable action, right? But it could be the case that you've got your tree set up and that there's some actions that never occur because you've got some sort of bug in your tree, right? And you don't actually, it's very hard to determine whether or not this action can never occur, right? Because you've got a bug in your code, right? Because it never occurs, so you never see it, right? And to make it occur, it could be a rare set of actions that cause the thing to occur, right? So debugging becomes really problematic. Memory is something that we completely ignored in our discussion, right? Your actions probably need access to information stored in the game somewhere, right? Similarly, actions might want to share information with one another. So you have to have some mechanism that lets this tree share information between the nodes of the tree, right? And so that's not so straightforward. Maybe in the next lecture, we'll talk a little bit about that. What else is here? Okay.
So I'm going to do my absolute best to sort of stick to what is actually, I think, sort of unique about our behavior tree and why we made certain decisions. Well, first of all, the first thing to say is, well, what is actually going on inside those boxes? Like, what kind of decision routine are we using? Two general approaches. You can say, well, the parent knows what kind of children are attached to it, and so it just explicitly says who gets to run, which is fine. That kind of works.
So that's what we're doing in our discussion, right? The parent knows what nodes it has. It runs them from left to right. Right? It might have some randomness in it, so it can randomly choose them. This is a problem that there's lots of children, and because you might want some logic that picks which child to run, right? So in other words, you don't want it to be completely random. You don't want it to be left to right, but rather there's some other criteria that you are using to decide which child should run, right? If there's lots of choices to pick from, the logic in the parent node becomes very convoluted, right, which becomes complicated. So you can try to solve this a different way.
So we generally go when we can for the sort of the child competitive model. Even within the child competitive strategy, though, you can sort of do two large-scale approaches, sort of the analog relevancy approach. And I've dealt with a lot of academic systems which have done it this way. Basically, each behavior provides some floating point number, which is how much I want to run. And then the parent says, okay, I pick the one with the highest number. And I probably give a boost to the guy who was running last time because I don't want to do it or something like that. That's good. That's good if you like subtlety, which as an industry and as a company we do not at all like. And in general, if we were using analog relevancy, we would generally want sort of discrete events to snap on authoritatively, and so we'd probably go from 0 relevancy to 5,000.0 relevancy from one tick to the next. But as long as we're doing that, well, why not just go ahead and do a binary relevancy? So in other words, each behavior is just saying, yeah, I want to or I don't. So once I have that, I have a couple of options open to me about how exactly my decision is going to go about. There's things like a prioritized list. So my list of children is prioritized. I pick the first one that is relevant, and on subsequent ticks, more relevant guys can, or more high priority guys can interrupt lower priority guys. There's things like you can do it sequentially.
So that's what we're talking about in our discussion here, right? So the children run sequentially from left to right. And there's a randomized one right there, right? But you can, if you can listen, you can actually understand and paying attention to what he's talking about. There's a lot more subtlety that you can put into these behavior trees than what I talked about in the lecture, right? So you can the information from the children can be from the child nodes can be communicated back to the parent nodes to inform which one of the child nodes should run. Right? It doesn't have to happen left to right. It doesn't have to happen at random. Oh, I think that's plenty here. So this is very long. So it's over an hour-long talk. It's one of the podium presentations given at GDC in 2005. So if you're interested in actually hearing more about what they're using, how their behavior trees work, you can watch the rest of that talk there. So that's linked right there. Okay, so behavior trees in actual game engines. So Unreal has them built in. Again, the Unreal behavior tree doesn't work exactly the same as what I described, although it's close, right? So here's their documentation for their behavior trees. You can see here that there's a picture of one of their behavior trees. So one of the reasons behavior trees are popular in game engines is that you can use a graphical editor to edit them, right? And this means that non-programmers can actually create these things, right? Eventually, the programmer has to implement the actual actions, right? The behavior that happens in the actions, but non-programmers can actually design the tree without having to be able to program, right? And this is all click and drag and sort of thing, right? And so there is a behavior tree. The purple nodes are your leaf nodes, so those are your actions, right? And your blue node, your internal nodes, these are your composite nodes. And so they talk about the basics of behavior trees here. They talk about something called the blackboard, which we'll possibly talk about in the next lecture. Here we go. Blue nodes these are your composite nodes. I'll tell you what decorators in the next lecture. Your purple nodes are your tasks, so their nomenclature is a little different. They call only the leaf nodes their task nodes. This is the problem when you're using behavior trees. Everybody calls stuff. Everybody uses a different name for everything, and one person's implementation of behavior tree could be very different than another person's implementation. So Unreal doesn't use condition nodes, right? Instead, they tell you to use something called a decorator instead. So the condition here you can see in blue, right? So in our behavior tree that has line of sight would be a leaf node over here somewhere, would be a leaf node down here, right? They've decided to include it in the parent node instead. And they have all sorts of good reasons for doing this. And then finally, they talk about the differences in their behavior trees compared to standard behavior trees. And so if you want to read more about that, you can read about the Unreal. You can read Unreal's documentation on their game engine there. Is anybody using Unreal or played around with it? Yeah, a little bit. It's a much more sophisticated engine than Unity. Okay, I think that's all I want to talk about for today. There was something. What was I? Oh, right, back here. So this idea of using a random sequence lets you create a sequence, not necessarily where everything is random, but where some steps are random. So here, the first step, something random happens, right? But that random sequence could go somewhere in between. Sorry, you could have a random sequence in between. So it doesn't have to be the first thing that happens. It could be one of the intermediate steps or tasks that occur, right? And so you can still have parts of your sequence be deterministic. So they run from left to right, right? But some of the other sequences do not necessarily run left to right. Right? And so this is what I've shown you in the lectures is an example of a relatively simple behavior tree that lets you produce pretty reasonable or pretty complex behaviors, right? But it's not as flexible as the behaviors you can get out of something like Unreal, or if you go onto the Unity store, you can find all sorts of implementations of behavior trees that let you do that are more sophisticated in how they run the child tasks. All right, so that's it for today. Tomorrow there's no lecture because I have a last minute travel that has to happen tomorrow afternoon, so I can't be here for the lecture tomorrow. So our next lecture will be Thursday, right? Thursday, right? Yeah. I think Thursday. So the next lecture will be on Thursday, and I'll post an announcement on it.